and start recording. Okay, awesome. And then there's a couple of things I want to change. Okay, so for today, I think this is probably one of the classes that students enjoyed the most because today we're going to be talking a lot about multiplication tricks. So I'm sure in many of your like number sense and things, you will see lots and lots of multiplication problems. So today we're going to talk about how to do many of those problems. Um, we're also going to talk about different strategies for multiplication, different scenarios and things. Sometimes we'll do proofs, but other times those proofs you can probably do a little bit on your own. So let's go ahead and get started. Let me go ahead and share. Okay, perfect. All right. Um, Cool. Actually, before we get started, I feel like we should do an icebreaker. I really need an icebreaker today, so we'll do a fun one. Um, okay. Uh, what food could you eat for the rest of your life? Okay, so if you could only eat one food, what food would you eat for the rest of your life? Let me know in chat, and yeah, we can take a look. Skip this over. Okay. Vaughn says chicken tenders. Yeah, chicken tenders are pretty good, especially if you get them at like a good place and the seasoning is good. Manit says candy. Oh man, I don't know if I could eat candy. Honestly, like I've been eating a lot of candy lately, and I don't know if I like it a lot. Um, Someone said pizza. Shrinika says pizza. I like pizza. I like pizza too. I feel like with pizza, there's a lot of ways you can go because of the toppings and stuff. So that's actually pretty good. I bet he says a salad to keep me healthy if I want to live that long. Wow, that's smart. That's smart. But I don't know if I could eat salad all the time because, like, oh man, I don't really like salads. They're kind of boring. But if there's like good dressing and stuff, I think I could do that. Okay, awesome. Divya says probably chicken salad since it has protein and nutrients. Okay. Wow, you guys are really healthy. I don't know if I would be this healthy at y'all's age. Sia says pasta macaroni. Um, Spaghetti and a lot of other toppings. Yes, I love I like pasta salad a lot. Like that's really good. But yeah, pasta in general is really good. I feel like you can get a lot of nutrition there. Sachi says healthy foods. Okay, awesome. Arena says pasta as well. Zombie says pizza. Arhant says his mom's food. Oh, that's really sweet. Yeah. Biryani, Natik says, that's funny. Abjuk says, I would just get pizza because I can put whatever I want on it. That's true. I think pizza has a lot of flexibility. Minnie also says pizza. Okay, awesome. Yeah, so some of y'all are actually really healthy. That's pretty impressive. I don't think I could make those healthy food choices growing up. So that's good that you guys are already on that path. Okay, awesome. All right, let's go ahead and get started with today's lesson. So we're going to start off with kind of a pretty big point. Today we're going to start off with a little bit of FOIL. Now, if you haven't heard what FOIL is, that's totally okay. FOIL, actually, I have a nice diagram here, so let me go ahead and paste that. But basically, FOIL stands for first, outer, inner, last. Um, There we go. That's now very easy to see. So what we do with FOIL is we kind of take like a two-digit number and we're trying to multiply that two-digit number um, in this kind of format. So a big part of FOIL is writing a two-digit number via its place values. So for example, if I had the number 45, I could break that into 40 plus 5. Or I could write that as 4 times 10 plus 5 times 1. So that's how I'm breaking it up into place values. Um, Similarly, if I had like 67. That would be 6 times 10 plus 7 times 1. So as you can see, I'm kind of like breaking it up into those place values. So FOIL helps me multiply by place values. So if I write my number, like let's say, let's actually do 45 times 67. I can write this as 40 plus 5 times 60 plus 7. Oh no. Oh, wait, hold on. Let me stop sharing really quick. Okay. And then let me go ahead and share again. Okay, there we go. All right. Hopefully you guys don't see any weird annotations now. Okay, awesome. So, start off once again. If we have 40 plus 5 times 60 plus 7, we're just going to do FOIL here. So I'm going to do my first terms multiplied together. So what's 40 times 60? 2,400. Thank you, Vivon. Okay, excellent. What is my outer terms multiplied together? So that's going to be 40. Oh, that was a very poor. Okay, 40 times 7. What is that going to be? 280. Thank you all so much. And then I'm going to do my inner terms together. So that's going to be 5 times 60. So what is that? 300. Very good. And then my last terms of 5 times 7, which is equal to 35. Good. So now when I add all of these up together, what do I get? Okay, Divyan says 3015. Sachi is also in agreement. Let's see. 2,700 plus 315. Yeah, I think I also agree. And it seems like most of y'all are starting to agree as well. So good. This seems to be our final answer. Good. So as you can see, instead of doing that like two-digit method, like this kind of setup, where you have to write down carries and you might make a mistake and stuff, FOIL is very easy to see. It's like all horizontal. You just go like in the order necessary, and then you just keep adding your different products. So yeah, FOIL is a very useful technique. You see it everywhere all the time, and this is probably one of our biggest multiplication tricks. So having this mastered is really, really important. So to start off, oh, that's not what I wanted to do. So to start off, let's take a look at some questions. So let's do a couple more questions and see if you guys have the hang of this. I'm gonna minimize the concept stuff really quick. Hopefully it's still visible, but I'm gonna minimize that for the time being. And let's do a little bit of practice. So let's do 23 times 54. And then let's do 40, 46 times 83. Or no, let's do 80, 89. And then we'll do, actually 2 is enough. Yeah. Okay, work on these two. I'll give you all like maybe 30, 45 seconds. And let me know your answers in the chat. Okay, for the first one, I'm seeing a lot of people getting 1242. So I'm going to write that down tentatively, and we can see together if that's actually correct. Does anyone have an answer for that second problem just yet? Okay, Vivon is getting 4094, and Manik got the same thing. So I'm going to write this down, but if y'all have other answers other than 4094, please share. Great. Yeah, I don't see any other different answers. So let's go ahead and take a look. So there's kind of like two ways you can think about it. Both fundamentally are the same thing, but people might like different ways. So I'll go over like both kind of varieties almost. So starting off with the place value working method, um, we can do 20 plus 3 times 50 plus 4. And so when I multiply, I first get um, 20 times 50, which is 1,000 plus 20 times 4, which is 80, plus 3 times 50, which is 150, plus 3 times 4, which is 12. So if I go ahead and add those all together, I get 1150 plus 92, which is 1242. Okay, awesome. Yeah, I absolutely agree with everyone there. So nice job with that. And then, okay, so this is like one kind of variety. On the second number, on the second problem, I'll show you guys like the other variety. So the other way we could do this is instead of breaking it up, we just kind of proceed in this fashion. So like we kind of just deal with the numbers as they are. So the way to do that is I'm going to first multiply my last digits. So 6 times 9 gives me 54. Now obviously I can't write 54 in that last digit place. I'm only going to write that 4. And so let me actually do this in a different color. I'll do it in purple. My last digit is 4, and then I'm going to carry a 5. So I'm just going to write like a little 5 up there. And then I'm going to do my inner and my outer. So I'm going to do 4 times 9, which is 36, plus 6 times 8, which is 48. So, and in case you don't see that, um, it's going to be 48, and then I'm going to add my carry of 5. So in total, when I do that, I should get 84 plus 5 is 89, and I'm carrying an 8. And then I multiplied my first term. So 4 times 8 is going to be 32 plus 8 is equal to 40. And those are my first two digits. And so that's another way I could look at this. So the second method doesn't actually break up into place value. It's a little bit faster, but you have to be really careful with the carries. The first method, you're writing out a lot of terms, so it's not the fastest thing to do on the number sense. But that second trick, you do definitely want to be careful. Um, okay, excellent. Thank you, Vaivehi, for putting in like that strategy of breaking up by place value. I think that's helpful for some people to see as well. Divyan says that they use the second strategy. Yes, I like to use the second strategy as well. But if you need to break it up into place values and do it that way to get comfortable, that's totally okay. I would recommend getting familiar with that second strategy though, because that's the one you're gonna use the most. Okay. Is everyone good on this, or do you guys want to do a couple more practice problems? This is pretty important, so if you want to do more practice, that's okay. Just let me know in the chat. Okay. It seems like we're pretty good on this. So let's go ahead and move on. Yeah, we're gonna talk now about one of my favorite tricks actually, because it's very, very simple. We're gonna talk a little bit about, well, actually, after I minimize this, we'll talk about it. Yeah, now we're going to talk a little bit about squaring stuff. So in particular, squaring numbers that end in a digit of 5. And so, oh, wow. Okay, there we go. Awesome. All right, now that that's all out of the way, let's talk about how to square a number ending in 5. So this is something like 45 squared, 195 squared, 5 squared, yeah, so things like that. So a couple of things to note, whenever you square something ending in 5, the result always ends in 25. So 2, 5 are always the last digits. And so for the first two digits, what we're going to do is we're going to take that tens digit and then multiply it by one more than itself. So for example, or actually, we can actually kind of go into a proof for this if y'all are interested. Yeah, let's do a quick proof. So if I have, let's say I have the number A5, where A5 is like the total digits. So like that's how we denote that it's a whole number. So like 45, 55, and in those cases, A is either 4 and 5. And so I'm squaring that. So I can break this up into place value as 10 times A plus 5 times 10 times a plus 5. And as you can see, because I'm multiplying two different kinds of place value bits, I can use FOIL here. So let's go ahead and take a look. If I FOIL this out, I multiply my first terms together. I get 100 times a squared plus my outer term times my middle term. And that's going to be 50 times a plus 50 times a is 100 times a plus 5 times 5, which is 25. And so if I group this all together, I will get 100 times a plus 1 plus 25. So as you can see, those last two digits are 25 because if I'm multiplying something by 100, that means their last two digits are 0, 0. So 0, 0 plus that 25 gives me those last two digits of 25. And then my first two digits are a times a plus 1, which is the tens digit times the tens digit plus 1. So that's a little proof of like where this like kind of idea comes from for squaring. So let's go ahead and take a look at a couple of examples. So to start off, can you guys tell me what 35 squared is? Let's do 75 squared. And as a little challenge, can you do 195 squared? Okay, so for the first one, I'm seeing a lot of 1225 for the first one. For the second one, I'm seeing a lot of 5625. And for the last one, I'm seeing people putting in 38025. Okay, awesome. I'll give you all, if you guys don't have any answers yet, I'll give you like maybe another like 5 or 10 seconds. But for the most part, I don't think anyone is deviating from these answers. I think a lot of people are getting these, which is good. That's excellent to see. Alrighty. Okay, so let's go ahead, take a look at some of these questions. So starting off with 35 squared, we can immediately write down those last two digits as 25. And then that first tens digit is 3. So 3 times 3 plus 1 is 12 because it's 3 times 4. So I get 12 as my front two and 25 as my last two digits. So 1225. Then if I take a look at 75 squared, once again, I'm writing that 25 down at the end. My tens digit is 7, so if I do 7 times 7 plus 1, that's 7 times 8, which is 56 for my first two digits. And then finally, 195 squared. So that 5 squared gives me a 25 at the end. And then I do 19 times 20, my front two digits, and then I multiply that by 1 more than those front two digits, so 20. So 19 times 20 gives me 380. So I get 38025. So as you can see, this trick doesn't apply just to two-digit numbers. We can also use it for three-digit numbers. And so that 195 squared is an example. I would just caution you because if I had instead asked you to do 175 squared, I don't think you would want to sit here and do 17 times 18. So just be a little careful about when you use it. But yeah, I would definitely say that you can use this for three-digit numbers. Okay, awesome. Any questions? No? Okay, it seems like we're doing great, which is wonderful. All right. Um, okay, let's go ahead and kind of zoom out from squaring and do a little bit about a little bit more multiplication, but like we're kind of still in that realm of, squares, because our next trick does use a little bit about kind of squaring. Okay, so now we're going to talk about how to multiply two numbers where the ones digits add to 10 and they have the same tens digit. So this is kind of a very specific trick. So if you're using it, be careful. Be careful that you meet all the conditions before you use these kinds of tricks. So the kinds of multiplication that I'm talking about in this case is 43 times 47. Is that color visible to y'all, or do you want me to, is it a little too light? It is light. Okay, yeah, that's what I was thinking, but I didn't know if it showed up better. Okay, here, let me kind of change the color, or at least like maybe thicken it. Oh, yes, okay, it looks better thick. Okay, cool. So, starting off 43 times 47. That's kind of what I'm talking about here. Because if you look at the ones digits, 3 times 7 is equal to 10, or sorry, 3 plus 7 is 10. So those last two digits sum up to 10. And then that front two digits are the same. So 4 is equal to 4. So we're going to talk about how to multiply all of these together. So first, to start off, we're going to multiply the ones digits together and write that as a two-digit number. So in this case, if I have 3 times 7, well, first I need my writing tool. Okay. If I have 3 times 7, what is that? 21. Excellent. So 21 is going to be my last two digits. And then if I have my first digit of 4, I'm going to do the same thing as I did with that squaring with 5. I'm going to take that first digit of 4, and then I'm going to do 4 times 4 plus 1. So 4 times 5 is going to be 20. And so this is my final answer. What do we think? Does that kind of make sense where this is coming from? And the proof to this is pretty much the same as what we did for the example with 45 squared, or for like the numbers ending in 5 squared. So if you don't like, if you're still like, what the heck, why are we adding all these numbers and doing this weird multiplication? Check out that proof, because that will make it a lot more sense. Okay. Divya, thanks so much, or Divya-san, thank you so much for putting that explanation in the chat. And yeah, I think a lot of y'all were already getting 2021 before I like even finished explaining, so I'm glad you guys can see the parallels in this trick. So let's do a couple of examples before we move on. So to start off, what is 61 times 69? And then we can do maybe like 30. Let's do 33 times 37. Cool. Okay, awesome. I'm already getting a lot of answers, which is wonderful. So for this last one, I'm getting 1221. I think I might have missed y'all's answers for the first one, but I'm now seeing 4209. Okay, awesome. Let's break this down. So to start off, for this first question, we take those last two digits, and that's 1 times 9. So 1 times 9 is 9. And actually, I didn't see this error here, but if we get a one-digit answer, we have to still express it as a two-digit number. So I can't just write 9, I have to write 09. And I think almost everyone here did that, so that is wonderful to see. But make sure that you do that going forward, because sometimes students will just write 9 and then they'll get a three-digit number when they should actually be getting a four-digit number. So in this case, we would write 09 at the end. And then for the front two digits, I have 6, so then I'm going to do kind of like 6 times 6 plus 1, so 6 times 7, which gives me 42. So 4209 is what I have for this first question. Okay, awesome. Now going on to the second question. This one's pretty similar to what we did in the practice, because it's the same last two digits, but if we have 3 times 7, that gives me the last two digits of 21. And then I do 3 times 3 plus 1, so 3 times 4, which is equal to 12. And so that's how I get 1221. All right, what do you guys think? Are you guys good, or do you want a little bit more practice for this trick? Good. Okay, awesome. I think this one's pretty similar to the multiplication by fives trick, or the scoring by fives trick. So hopefully that makes sense. And actually, if you want to take a look, let's say we did like 45 squared times 45 squared. It's actually literally the same thing, because if you think about it, those last two digits do add up to 10. 5 plus 5 is 10. So if I really did want to do this, I could do the last two digits, 5 times 5, I get 25. And then my first two digits, I would get 4 times 4 plus 1 is 20. And so this trick is very, very similar to scoring with fives. So hopefully you guys definitely see the parallels here. Okay, awesome. Let's take a look at our next idea. But first, let me minimize this so that way we have space. All right. Okay, so now we're gonna we're gonna kind of grow bigger picture. Now, instead of multiplying two numbers with the same for tens digit and like summing to 10, all those specific conditions, we're gonna talk about multiplying two numbers close to 100. So still an important condition, but definitely you have a lot more flexibility here. So the kinds of problems that I'm talking about in this scenario, but first let me change color are like, for example, 97 times 94 is a sample problem. So the general idea here, and once again, you can always verify this with FOIL. The proofs are in the handouts that we give after class, but you are definitely welcome to check out the proofs on your own. The general idea, we want to first start by finding the differences of each of the numbers from 100. So I'm going to write the differences in, let's do, what color have I not used? I'll do a teal, like a teal. Okay, so how far is 97 from 100? 3, good. It's minus 3 away. And what about 94? How far is that from 100? It's minus 6 away. Good. Okay, so what I'm gonna do is I'm gonna take this difference and subtract it from the opposite number. So because it's 97 is 3 away from 100, I'm gonna do 94 minus 3. And so that'll actually give me my front two digits. So 94 minus 3 is 91. And then I just have to add the last two digits at the end. So to find the last two digits, I'm going to multiply my differences together. So 3 times 6 are my differences. So 3 times 6 gives me 18. And so that's my final answer, 9118, which I already see many of you putting in the chat. So wonderful, wonderful job there. Okay, excellent. Yeah, so just to like recap, as you can see here, we're kind of like the big idea here is using the differences, and with the differences we're able to get our final answer. Now I know I said I did 94 minus 3, but I'm sure some of y'all noticed that you can definitely do 97 minus 6 to get the front two digits. It does not matter. The point is you're subtracting the difference from 100 for one number from your other number. And that's your key idea to get those first two digits. Okay, so let's take a look at a couple of other examples, and then we'll talk about like probably the best range to use this in. So let me go back to my nice dark blue. We can do 96 times 98. And then I'll make this a little difficult for y'all and do a pretty nasty one. We can do 87 times, let's do 93. Yeah, that's good. Okay, cool. So for the first time, I'm seeing people saying 94, 48. Okay, I think, all right. And for the second one, I'm seeing people say 80, 21. I don't think I see any different answers. But if you do have a different answer, feel free to, add that in. Okay, let's take a look. So starting off with this first one, the differences. Let me go ahead and add a little bit of space for me, actually. All right. So from 196 is 4 away. From 198 is 2 away. So I'm going to do 96 minus 2 or 98 minus 4 to get those front two digits of 94. And then I actually disagree with this. I'm actually going to multiply those last two digits together to get 4 times 2, which is 8. So I'm going to once again write that as a two-digit number. So instead of writing 48, I should be writing 08. And then that is an answer I would agree with. So 9408. Does that make sense? I don't know who put 9448 in, but does 9408 make sense? Yes. Okay, awesome. All right, let's take a look at 87 times 93. I think there's a little bit of a disagreement in the chat. So I'm seeing 8021 and also 8091 as the two answers. So let's go ahead and determine which one is actually correct. So to start off, um, once again, my differences. So this one's a tricky one, and I mean, 87 is close to 100, but it's definitely not very close. So like, yeah, this is something that we'll talk about after solving this. So 87 is going to be 13 away from 100, and then 93 is 7 away. So 87 minus 7 or 93 minus 13 gives me my first two digits of 80. So that's where the 80 comes from, and I think we were all in agreement there. So great job. Now I'm going to multiply those two differences together. So 13 times 7 gives me 91. And so I get my last two digits of 91. So 8091 is correct. Aradi, I saw your little celebration there. So that's awesome. But yeah, 8091 is correct in this case. Now, for those of y'all that were putting in 8021, be careful. I think what you did was you did 3 times 7 instead of 13 times 7. But remember, we're always taking the product of the differences. So that's why it's 13 times 7 and not just 3 times 7. But good. Okay. Hopefully that trick made. Can you repeat the 80? Yes, I can. So to get that 80, we're subtracting the difference from 100 for one number from the other number. So for example, I would do 93 minus 13 and and 13 is that difference for 87. So 93 minus 13 gives me 80. I could also do 87 minus 7 to get me 80. But hopefully that makes sense to F41632. Okay, awesome. Did anyone have any other questions? No, okay, I don't see anything just yet. So let's go ahead and move on. All right, so we talked about, actually, before we move on, um, sorry. One thing I did want to talk about is the range to use this in. So you saw in that last problem, 87 times 93, it was possible to use it, and I know most of you all know that 13 times 7 is 91, so it's okay to use it there. I honestly wouldn't multiply, I wouldn't multiply by anything lower than 85. So 85 times 85 is the cutoff. I really wouldn't be going beyond that. Because once you do, you're gonna start spending more time on figuring out what those differences multiplied together are, and the trick won't be as fast as it's meant to be. And so that's why I wouldn't recommend using this for two numbers that are below 85. If it's like kind of near 85, it is possible, but do not go below that because otherwise it's going to be pretty hard for you to find the product of the differences. Okay, awesome. So on a similar theme, since we talked about how to multiply two numbers that are kind of below 100, let's now talk about how to multiply two numbers that are above 100. Um, so to start off, I'm sure many of you guys can find the parallels between the two techniques. But to start off, let's take a look. So the kind of things I'm talking about is 103. Oh, that's this very slanted 103 times 107. So, to start off, once again, find the differences. Finding the differences is key. So I'm gonna do, in this case, I'm 3 over here, and I'm also 7 over here. So what I'm gonna do is I'm first going to add the difference for one number with the other number. So in this case, 103 plus 7 gives me 110. And now similarly, I could do 107 plus 3, it also gives me 110. And then those are going to be my first three digits. And so my last two digits are going to be the product of the differences. So 3 times 7, which gives me 21. So as you can see, this trick is very, very similar to what we did previously. The proof is also very similar. So yeah, I think this one is very intuitive. So let's go ahead, jump straight into a couple of examples. So let's do 112 times 114. And then a little bit easier, we can do 104 times, let's do 108. Yeah, 108 looks okay. Or actually 109. I'll do 109. Yes. And then the same rules apply for those last digits. If you ever get like a one-digit number, make sure to write it as a two-digit number. If you ever get carries, don't forget to include the carry. But yeah, all that jazz, same rules apply. All right, for the first one, I'm seeing a lot of people saying 127, 68, I believe. And for the second one, I'm seeing a lot of people saying 11336. And I don't think I see any variation, but I'll give people a couple more moments to put those answers in, just in case. Okay, awesome. So I think we're honestly pretty much in agreement over these answers, but let's go ahead and break this down. So starting off with this first one, which is pretty tricky, we're gonna find the differences as always. So to do that, first I'm gonna create some space for myself, and I'm gonna write the differences in a dark green. Or actually, we already used dark green. I'll write it in this like weird, ugly green. Okay, so to start off, 112 is, 12 away from 100. And then 14 is 14 away from 100. So I'm going to start off by subtracting one difference from the other, or sorry, adding differences. So 114 plus 12 gives me 126. So I'm going to write that down tentatively. Now, I know I'm going to have some kind of carry because both of my differences are greater than 10. And so if I multiply two numbers greater than 10, obviously I start getting into that hundreds range. So if I do 12 times 14, there's a couple of ways you can do this. I would personally do like, there are two numbers centered around 1. So I would do 13 squared minus 1. I know 13 squared is 169, minus 1 is 168. So I write my last two digits of 68. But I only have space for 2 digits, not 3. So that extra 1, that hundreds digit, I have to carry over to the rest of my numbers. So that's why I do 126 plus 1 to get 127. And so that is my final answer. As you can see, carries are super duper important. Now, this trick was okay in this scenario because I could easily find 12 times 14. But once again, I wouldn't use this for anything that's bigger than like 115 times 115 because then your multiplication starts getting a little bit tricky. So yeah, this I would save it for numbers in that range. Okay, hopefully that made sense. And then we'll take a look at this easier example of 104 times 109. So to start off, 104 is 4 away from 100, and 109 is 9 away. So if I do 104 plus 9, I get my first three digits of 113. And then I multiply my differences together. So 4 times 9 gives me 36, which is my last two digits. So 11336 is my final answer. Okay, I know that was quick, but it seemed like most of y'all already got the hang of it. But if you guys don't understand like where some of these numbers are coming from, let me know. Send me a question in the chat. Feel free to raise your hand. But yeah, I'll give you guys a moment if you need to type anything out. Okay, as you can see though, this trick is very, very similar to something we already did before, so hopefully it's not like too groundbreaking, too difficult. But yeah, I think most of y'all have already got the hang of it. Okay, I am not seeing any questions, so I'm going to go ahead and move on. If you do happen to think of a question, feel free to ask me after class. But in the meantime, yeah, let's go ahead and move on. Okay, so to start off, our next trick, so we talked about multiplying two numbers above 100, two numbers below 100. Let's talk how to multiply two numbers where one is above 100 and one is below 100. So the kind of problems I'm talking about in this scenario are kind of like in the form 93 times 104. So times 104. Sorry. Okay. So as you can see, 93 is below 100 and 104 is above 100. So this is the kind of like situation here. So once again, we find the differences from 100. We are always, always, always finding differences. So that's going to be our first step. I'm going to write this first step in kind of like an orange. And so 93, the difference here is -7. And then for 104, it's +4. So these are the differences from 100. So I'm going to subtract one more than the difference for 93 from 104. So in this case, I'm going to do 104 minus 7 plus 1. So 104 minus 7 plus 1. One more than that difference, the negative number. And so when I do that, I get 96. And then I'm going to do 100 minus the product of the differences. So 7 times 4 is 28. So 100 minus 28 is equal to 72. Okay, awesome. And then I put that together to get 96.72, like many of you are already saying in chat. So wonderful work there. This technique is a little bit more work, just given the fact that there's like a bunch of different signs involved. But as you can see, very similar thinking process. So to recap what we did here, we once again found the differences from 100 first. That is the first step in any kinds of problems surrounding numbers or regarding numbers surrounding 100. We took the difference. So for the number that was less than 100, we took that difference, we added 1 to it, so 7 plus 1 to get 8, and then we subtracted that new value from 104, from our number that is greater than 100. So 104 minus 8 gives me 96. And then to get the last two digits, I would do the product of the numbers, the product of the differences. So 7 times 4 is 28. But instead of writing down 28, I would subtract from 100. So 100 minus 28 actually gives me 72. Okay, awesome. All right, so actually, I guess I can say this later. Let's take a look at some questions first, though. All right, let me move this all up. And let's use a nice purple. Okay, so some other questions. Can you guys do 108 times 95? And can you guys do 112 times 92? Give you guys a couple of minutes, or not a couple of minutes, but like a couple of seconds, maybe close to a minute to do this. Yeah. Cool. Cool, cool, cool. So for the first one, I'm seeing a lot of people saying 10260. Okay, cool, cool, cool. Uh, All right. Does anyone have any answers for that second one? Oh, okay. I see Manit said 10304. So did Atharv, and so did Avrina. Awesome. Oh, lots of A names tonight. That's cool. 10304. Excellent. Okay, let's go ahead, take a look at each of these problems and see if the answers that you guys said are correct. I think most of y'all are giving the same answers, which is good to see that at least we're in a consensus here. Okay, so to start off, we always start off by finding the differences. So let's go ahead, find these differences. In this case, I'm 8 over, and in this case, I'm 5 under. So I do 5 plus 1 to get 6, and then I do 108 minus 6, and that gives me my first three digits of 102. So that part is correct. And then for my last two digits, I have 8 times 5, which is 40. I do 100 minus 40 to get my last two digits of 60. So you guys are absolutely correct in this regard. And then moving forward, for the next part over here, I'm 12 over here, and I'm 8 under here. So I do 8 plus 1 is 9. If I do 112 times 9, or sorry, 112 minus 9, I get 103. And then if I do 12 times 8, I get 96. 100 minus 96 gives me 0, or it actually gives me 4, but don't forget, I have to write my number as a two-digit number. So I can't just write down 4, I have to write down 0, 4. And so that's where I get this final answer. So I absolutely agree with y'all on both of these parts. So wonderful, wonderful job here. Now for this trick, if you do get a number, like if your product of the differences is over 100, you do have to like kind of do a little carry situation and subtract one extra from your like three-digit part. So it can be kind of tricky. That's why I wouldn't recommend using this if your like differences are super big from 100. But it is certainly possible. It's just a little more difficult because you have to be very careful with the carry situation. So yeah, I kind of want to avoid that for the time being, but it is definitely possible. So yes. Okay, cool. Any questions for this method? Any questions? No questions. Okay. Awesome. Is everyone doing okay so far with all these tricks? Do they all make sense? Um, okay, cool, cool, cool. That's good to see. Okay, Sachi asked, can you do the same thing for 1,000? Yes. So all three tricks we just talked about, multiplying numbers less than 100, multiplying numbers greater than 100, multiplying with one below, one above 100, all of this applies for 1,000 as well. It's literally the exact same rule repeated, except now instead of 2 digits, we're using 3 digits. But yeah, very, very similar stuff. Okay, awesome. All right, let me get a kind of quick preview here and make sure we're doing okay time-wise. Alrighty, awesome. Okay, yeah, I think we have time for maybe like two, maybe three more tricks. But let's see where we get. Okay, so to start off, remember before how we talked about how we could square two numbers ending in 5. Let's now talk about what it means to multiply just two numbers ending 5. Any two numbers ending in 5. So what we want to do, and once again, there's a proof of this in the handout, so if you guys want to check this out after class, you are very welcome to. But the idea here, it actually kind of varies a little bit based on the tens digits. So we're going to talk about two different scenarios. So first, let's take a look at 45 times 65. Now, what's important here is that both of my first two digits are even. That means they both are divisible by 2. And so in this case, what I'm going to do here, or actually, they're also the same parity. So when I say parity, I mean like, is the number even or odd? So in this case, because 4 and 6 are both even, they both have the same parity. And so in this case, what we're going to do, if the first two digits are the same parity, we're going to start off by looking at the last two digits. And if the first two digits are like both even or both odd, they have the same parity, my last two digits are going to be 25, just 25. And then my front two digits, I'm going to multiply 4 times 6, and that gives me 24. And then I'm going to do 4 plus 6 divided by 2, so taking that average. So 4 plus 6 is 10, divided by 2 is going to be 5. And so 5 plus 4 times 6 is going to be 29. So our final answer is 2925. Awesome. Now let's take a look if the parity is not the same. So for example, let's do 35 times 85. So as you can see here, 3 is odd and 8 is even. So those parities are different. Now, when the parities are different, our last two digits are not 25, they're actually 75. And so we'll do the last two digits as 7, 5. And then for the first two digits, it's kind of the same process. We're going to do 3 times 8, which is 24. And then I'm going to take the average of 3 and 8, but I'm going to ignore the remainder. So 3 plus 8 is 11. Now, if I take 11 divided by 2, I get 5 with a remainder of 1. But like I said, I'm going to ignore that remainder. So I'm just looking at that 5. And so I'm going to add that 5 to the product of 3 and 8. So 5 plus 3 times 8 is going to be 29. So yeah, that's once again my final answer for 35 times 85. Now I know a couple of people are asking to repeat the first one, so let's go over that very quickly once again. So in this case, 45 times 65, 4 and 6, those front two digits, the tens digits, have the same parity. They're both even in this case. And so because of that, I know my last two digits have to be 25. My last two digits are 25. And then because of that, I'm able to do the front two digits. For the front two digits, I can do 4 times 6 plus 4 plus 6 over 2. So 4 times 6 is 24, plus 4 plus 6 is 10 over 2, which is 5. And so this gives me a final answer of 29. So you might be wondering, like, why are we taking the average of the front two digits? Like, what is the purpose of that? And the proof is actually in the handouts. We unfortunately don't have time to get through it right now, just because I want to get through a couple more tricks. Yeah. Okay, so Sachi asks, can you do this trick only with 5 in the ones place? Yes. So this only applies if my last digits are both 5s. And then as you can see, there's two cases. Either the parity for the first two digits are the same or the parity is different. Okay, what do you guys think about this trick? Does this make sense? Yes, yes. Okay. I think Vaibahi asked, can this work with a three-digit number? Yes, it can, but it's just difficult because then your front two digits are gonna be two-digit numbers multiplied together. And so that's kind of a lot of work. So we don't really use this for three-digit numbers. We kind of like only use it for two-digit numbers because it's a little easier. Okay, so I feel like a lot of people are saying foil is faster. Sometimes foil can be faster, but sometimes these tricks are actually a little bit more faster. You just need more practice with them. Foil can kind of get a little tricky with like carries and stuff. That's why that's why I prefer for y'all to find like the other tricks before you resort to foil, because sometimes foil will be a little slower. It might feel like it's faster just because you do it so much, but once y'all start practicing some of these more like unique and niche tips, these will also become like secondhand nature to you. So Vivehi also asked, can you use the add 10 units digit? Oh, I don't know what that is. Can you add a little bit more detail? Okay. And then while they're doing that, um, let's go ahead and move on to cut probably or actually no, I think we might have time to do two different topics. Okay, so let's go ahead and move on to squares. So let's talk about square numbers. Um, And now we did do a little bit of discussion with squares, mostly at the beginning of class, but there is definitely a lot more to squares. So let me first see if I can actually minimize this. Oh, no, this strategy is different from the one where, yeah. So in that case, that like where the units digits add to 10, the example Vaibahi provided will not work in that case because the front two digits are not the same. So I wouldn't use that for like where the front two digits add up to 10. And for the trick that we just did, it will not work as well. Just because the algebra becomes a little bit wonky, it won't work out. But yeah. Okay, good question though. Good question. Okay. I think Sachi asked, are we going to do any tricks with division? Unfortunately, there's not many tricks for division. You can definitely learn to estimate, but there is not very many tricks with division. You kind of just have to, do some long division there. But multiplication, we can definitely find some tricks. With division, I think the biggest thing is divisibility rules, which you did talk about last class. Once you get those divisibility rules done, I think that's probably the best you can do. But beyond that, division is hard to find tricks for. Okay, awesome. So let's go ahead and talk about some squares. Um, so I would say, first of all, I would first of all recommend you guys to at least remember your squares up to 20, and definitely you should remember them up to 30. That comes up a lot, but at the bare minimum, learn them up to 20. And then if possible, go up to 30. So yeah, the thing with squares that I really want to talk about tonight is a little bit of a pattern. So to start off, let's go ahead, and actually this might be our last topic because I don't want to rush anything. So let's go ahead and start off with, let's go ahead and look at 2 squared. All right, so I'm going to try to express my square in terms of the previous square. So before 2 squared, I have 1 squared. Now, is there anything I can add to 1 squared to get to 2 squared? What do you guys think? Okay, Avik says 3. Awesome. Yes, yes, yes. I can absolutely add 3. Thank you, Manit and Adar. I can add 3 as well. Okay, good. Now, let's say I have 3 squared, and I want to add 2, and I want to get from 2 squared to 3 squared. What can I add in this case? I can add 5. Good. All right, now let's say I had 4 squared, and I'm starting off from 3 squared, and I want to get to 4 squared. What can I add in this case? 7. Good. Now, can I rewrite 3 in terms of 1 and 2? Is that possible? Let's go back to that first example. Is it possible to write 3 in terms of 1 and 2? Okay, Vivon says yes. How can I write it in terms of 1 and 2? I promise it's not a trick question. It's as easy as you think it is. 3 in terms of 1 and 2 is just 1 plus 2. Good. I think, Audrey, you almost had it, except instead of 1 plus 1, it's 1 plus 2. Good. Now, Oh, and also thank you, Yvonne, for adding that just in. All right. Can I write 5 in terms of 2 and 3? What do you guys think? Use the previous format if you're a little confused. How can I write 5 in terms of 2 and 3? I just summed them, so I would do 2 plus 3. Good. Okay. Um, Now let's take a look at 3 squared. Can I write 7 in terms of 3 and 4? Yeah, I would just do 3 plus 4. Good. So as you can see, every square I can express in terms of like the number that I'm squaring and the number below it. And so this is actually pretty interesting. You might be wondering like, okay, this seems not very significant. But this is interesting because it helps us find some additional squares. So for example, if I want to find out 36 squared, I can just use 35 squared plus 35 plus 36. And 35 squared, I can do just like that because I know how to square numbers ending in 5. And then all I have to do is add a 35 plus 36 to that number. So let's kind of take a look at why this is true. There's definitely an algebraic way to do this, but that's kind of boring. So let's look at a fun geometric way. So to start off, um, let's draw a square. Okay, so I've got a nice little square. I'm gonna do a 2 by 2 square. Um, and right now I want to try to like get this to a 3 by 3 square. So to get to a 3 by 3 square, I'm gonna increase over here by 2, and I'm gonna increase over here by 2. Okay, but obviously that's not a square. I have to add in this little corner piece over here. And that now with that purple addition, that's a 3 by 3 square, right? So 3 squared over here is equal to that 2 squared. That's the green square I initially started with. That 2 squared. And then we can kind of think of it like this. In this case, I'm adding a 2 over here. So plus 2. That's where plus 2 comes from. But I also have to add in the 3 over here. Now, no, I'm not just adding 2. I'm adding 2 plus 1, that additional corner piece that finishes the square. So 2 plus 1, that gives me that 3 term over here. So it's kind of like a geometric way to think about like, okay, how am I even adding all of these numbers together? So let's see if we can construct 4. So I have my 3 by 3 square. It's a little lopsided, but it's definitely a square. Um, and then I'm going to add my next layer on top of it. And to my next layer, I'll do it bread. So I'm going to add the 3 terms over here. 1, 2, 3. And my 3 terms on this side as well. 1, 2, 3. And then don't forget my corner piece that makes it look like an actual square. So for 4 squared, this is actually a 4 squared now. I have 4 squared is equal to the 3 squared that we started off with. And then I added a total of 7 pieces. But I can write that as this 3. I'm adding these 3 pieces, and then I'm adding on the side these 4 pieces, 3 plus 4. And so that's how I get to 7. Okay, so yeah, that's kind of like a geometric proof of why this works. If you like the algebra proof, you could definitely check it out like that as well. But this is pretty important because we're able to find lots of different square numbers using kind of this strategy, and using squares that we already know, we can find some consecutive squares beyond that. So if you know, for example, if you're familiar with squaring numbers that end in 5, it becomes very easy to kind of find like different squares around that. So for example, if I know 35 squared, I can find 36 squared at 37 squared, and I can also find 34 squared at 33 squared because this trick works in reverse. It's the same thing except I'm using subtraction instead. Like for example, for 3 squared, I can represent that as 4 squared minus 3 minus 4, and then I'll get 3 squared. Okay, awesome. Yeah, so like Vinith says, we can do that. 69 squared is 4761, because we can do 70 squared minus 69 minus 70. So excellent idea there, Manit. Yeah, awesome. Okay, yeah, so this definitely can come in handy if you're trying to find some squares above 100. I would stay away from foil in cases like this because it's actually probably easier to use this trick instead. But yeah. Okay, awesome. So it is 9 o'clock. So let's go ahead and end here for today. Yeah, if you guys have any questions, feel free to stick around. But hopefully, you learned something new as always. And if not, we'll definitely find you something to learn going forward. But thank you all so much for joining me tonight. I hope this was a useful session for y'all. And if you have any questions or like concerns or anything, please do stay behind and ask me. I will see you all next week. Bye, everyone. Okay. So Sachi asks, what if you have a diagram and you have to figure out how many squares there are? You can just multiply, right? Because I know this is 4 by 4, so I can do 4 times 4 is 16. That's 16 total squares. I don't know if that was your question or not, but maybe I misunderstood. So if you wanted to clarify. Awesome. Bye, Raji. Bye, Natik. Okay. Bye, Arena. Bye, Sachi. Thank you all so much for coming tonight. Okay. I think Divyan asked for the algebra equations. Yeah, let's go ahead and take a really quick look at that. I'm gonna speed run this. Okay, so if I want to do a plus 1 squared, I can do that. This is a squared plus or actually, hold on. Let me do it this FOIL way, so that way, if you guys don't know the binomial expansion, you can do that now. So a squared plus a plus a plus 1 is equal to a squared plus a plus a plus 1. So as you can see, very quick proof there of where like this is even coming from. So for example, if I had 3 plus 1 squared, this is equal to 3 squared plus 3 plus 3 plus 1, which is 4. So 3 plus 4. So that's another way to kind of look at this. Yeah. Awesome. You're welcome, Nibia-san. Okay, bye, 19. And thank you, Raji. Thank you, Natik, for attending today. You guys were great in class, and I hope you learned a lot. Okay, see you all next week. Okay, Vaivehi, I think you asked, I need help with the question, what are two squares that differ by 999? Can you give me an example of what you were talking about? And if you want to unmute, you're welcome to, since I know no one else is here. All right, I have to ask you to unmute. Just kidding. Okay.
Like two consecutive integers that like differ by 999. Like you know how like one square is 1 and two squares like 4 and their difference is 3. And then they
Yes.
keep like increasing by 2. Like what would be like two squares that like differ by 999 that are consecutive?
Well, okay, if they're consecutive, can they differ by 990? Oh, are you saying like a squared minus b squared is 999?
Yeah.
Oh, okay, okay. Let me even think if that's possible. Um, yes, I think it is, but let me just check really quickly.
It was
Um,
like a Beast Academy.
yeah, I bet it was. I do like to ask questions like that. Okay. I think you could do, okay, so this works. If you do 32 squared, and I'll tell you how I got this, but if you do 32 squared minus 5 squared, that should be equal to 999 if you want to check that. Um,
Okay.
yeah. Okay, so the way you can kind of do this is by factoring. So you got to do a little bit of factoring here. So I believe we have talked about this, but if we haven't, an important factorization to know is that a squared minus b squared is equal to a minus b times a plus b. Okay, and so what I want to do is I want to express 999 in terms of two factors, right? And the goal is for those two factors to have an even sum, because if the factors have an even sum, I can do a minus b and a plus b, kind of treat it like a systems of equations. And when I add those two up, I get 2a. So the goal is for those two factors to have an even sum, so that way I can evenly divide by 2 and find my value for a. So right off the bat, I know that 999 is equal to 37 times 27. And that's just because like of a bunch of multiplication tricks that I have done, I'm able to find that really quickly. Now, if you didn't know that, that's okay. One way that you could find that is um, by doing a little bit of factorization. I mean, obviously 999 is divisible by 9, so you could definitely work your way from
Yeah.
there. And actually, because it's divisible by 9, there is actually another solution. So let's look at the divisibility by 9 as well. So let's say, well, 999 is equal to 9 times 111. So obviously my difference has to be smaller than my sum. So let's say this difference is 9 and this sum is 111. So if I add these together like a systems of equations, I get that 2a is equal to 9 plus 111, which is 120. So what is a equal to?
60.
Good. And then can you tell me what b is using one of the equations?
Um, oh, 50, 51, yeah.
51. Good. And so that's another pair that works. I can do 60 squared minus 51 squared is 999. Now, to my knowledge, I don't, okay, I mean like consecutively, you could do I guess five 500 squared minus 499 squared.
Okay.
And you can only get like so if you're looking at consecutive squares, the difference always has to be odd, because one has
Yeah.
to be even and one has to be odd. So like the total difference is definitely odd. And so if you're trying to look at the problems like that, to find the two consecutive squares, I would add one and then divide by two to find the larger square. Or you could subtract one and divide by two to get the smaller square. Either way works. But yeah. Okay, hopefully that answered your question. I know that was a little bit of a long explanation, but very good question. That was a very good question.
Thank you.
Of
Bye.
course. Bye. Have a good night.
You too.
Thank you.